Dear students, today we'll see the 8th part of ECD lab, in which we are going to see a few features of semiconductors. So let's start with the session semiconductors, and in this first point we will see, as we have already studied atomic structure in our last theory, so now we will see what do we mean by covalent bond. So here are the contents what we are going to see in this session. Number one is a covalent bond. Number two is a creation of hole. Number three is definition of semiconductors. Number four is effect of temperature on semiconductors. Number five is a classification of semiconductors. Number six is intrinsic semiconductor. Number seven is doping. Number eight is extrinsic semiconductor. Ninth is N-type semiconductor. 10th is P-type semiconductor. 11th is formation of Pn junction. 12th is biasing of diode. And 13th is effect of temperature on diode conduction. All these points which are related to semiconductor, we are going to study today. So let's start with the first point. What is covalent bond? So here, a covalent bond, definition wise, if you see, the outermost shell of any atomic structure has the valence electrons. If you see any atomic structure, the outermost shell, the outermost orbit will have the electrons which are named as valence electrons, which are loosely attached to the nucleus. Such an atom having valence electrons, when brought close to other atom, the valence electrons of both these atoms are combined to form an electron pair. This bonding is called as covalent bond. So here, if you see, we know that we had studied atomic structure like this. Say, if the atom is having 14 electrons, there will be nucleus, there will be orbit 1, orbit 2, and then orbit 3. Okay, so this is having 14 electrons, so there will be 14 protons here, neutrons, and then you have 2 electrons in the first orbit. You have 8 electrons in the second orbit, 4, 5, 6, 7, 8, and then remaining 4 electrons in the last orbit. Remaining 4 electrons in the last orbit. These 4 electrons in the last orbit are called as valence electrons. Okay. Now, many such atom. Now, this is one atom. Many such atom, if you combine, then the pattern will look like, say you are having one atom here, okay, and then you are having one atom here, then you are having one atom here, then you are having one atom here, then you are having one atom here. Okay, now this atom will have its 4 valence electrons. So 1, 2, 3, 4. This will have its 4 valence electrons. 1, 2, 3, 4. This will have 4. 1, 2, 3, 4. Or this will have 4. 1, 2, 3, 4. This will have 4. 1, 2, 3, 4. Now, if you see this pattern, now this is how the center atom is connected to all other atoms. You can see this. Okay, so here also you can draw like this. So when you have many atoms together, the pattern will look like this. If you see this atom here, now this atom is having 4 electrons, which are valence electrons, these 4. Okay, now each valence electron will make a bonding with another valence electrons of the other atom. So here you can see this is a bonding, this is a bonding, this is a bonding, and this is a bonding. This bonding is called as covalent bonding. Then we'll take an example to explain a covalent bonding. We know that we have two semiconductors. One is named as silicon, which has 14 electrons, and one is named as germanium, which has 32 electrons. So here, as an example, we will take germanium atom. Germanium atom has 32 electrons, out of which the 2 electrons will be in the first orbit, 8 electrons will be in the second orbit, 18 electrons will be in the third orbit, while the last orbit will consist of 4 electrons. So if you add them, 2 plus 8 plus 18 plus 4 is equal to 32. So the last orbit is having 4 electrons. These 4 electrons are valence electrons of germanium atom. These electrons tend to combine with valence electrons of the adjoining atoms, atoms which are next to it, to form the electron pairs. So how this happens, we'll see. So here you can see you are having a germanium atom here. So center also you have shown a germanium atom. So here you have shown a germanium atom which will be having 4 valence electrons, 1, 2, 3, 4. Now this will be joined with another germanium atom. That germanium atom will have 4 valence electrons, as I have told you earlier. Similar here, you can have a germanium atom. This will have 4 valence electrons. Similarly, here you have a germanium atom. This will have 4 valence electrons. Similar case will be here, and similar case will be here, and similar case will be here. So this pattern you can see. So these electrons which are going to form the bonding are the valence electrons, and the bonding which they form, this is the bonding, one valence electron with another electrons, and here also you can see there is a bonding. Here also you can see there is a bonding. So this bonding is called as covalent bonding. This is called as covalent bonding. Covalent bonding. Okay. Next we'll see what is the meaning of a hole in the concept of semiconductors current conduction. Whenever we say there is a current flowing, the current can either flow due to electrons or due to hole. Then what is that concept of hole which we'll be using always? So here we can say that due to a thermal energy supplied to the crystal pattern, the pattern of all the atoms what we saw together is called as crystal pattern. Now if you apply, or if there is a increase in thermal energy, some electrons tend to move out of their place and break the covalent bond. So whenever you have this covalent bond like this, say if you take again example of germanium, and one more atom here, germanium, and there is a covalent bond. There is one valence electron here and one valence electron here. Now when a temperature increases, okay, then one of these electrons tend to move out of their place and break the covalent bond. This electron can come out and break the covalent bond. Okay. Now once this electron has come out, that means that particular place is not having electron. Okay, so electron is here, but this electron has come out. This is germanium atom. This is germanium atom. So here there will be a vacant place of electron. This vacant place of electron can be treated as a positive charge. Positive charge, because electron itself was negative charge. So when negative charge has gone out, this vacant place can be treated as positive charge, and that vacant place, that is absence of electrons, is called as a hole. Okay. So here if you see the definition, due to thermal energy supplied to the crystal, some electrons tend to move out of their place and break the covalent bonds. These broken covalent bonds result in free electrons which wander randomly. Those free electrons can move, but the moved away electrons creates an empty space or valence behind, which is called as hole. That empty space of electron which is left behind is called as hole. So here this is called as hole. This is called as hole. And because electron was negative charge, this hole can be considered as a positive charge. This hole, which represents a missing electron, can be considered as a unit of positive charge, while the electron is considered as a unit of negative charge. The liberated electrons move randomly, but when some external electric field is applied, these electrons move in opposite direction to the applied field. But the holes created due to absence of electrons move in the direction of the applied field. That means whenever an applied field is given to this material, okay, then the movement of electrons, if you say the applied field or the applied voltage is plus minus like this, okay, plus minus like this, and here you are having your material, to that you are going to apply, and if that material is having electrons, if the material is having electrons, electrons will be attracted towards positive terminal and they will move like this. So this will be the direction of movement of electrons. If there are holes, then holes will be attracted towards negative terminal. Holes will be attracted towards negative terminal and they will move like this. That means holes will move from higher potential of the battery to the lower potential of the battery. Okay, whereas electrons will move opposite to that. That is what we have to see always whenever we connect the semiconducting material to a voltage. Then we'll go to see what do we mean by semiconductor. Now, semiconductor is a substance whose resistance of the material, lies between the conductors and insulators. A property of resistivity is not the only one that decides a material as a semiconductor, but it has few properties as follows. Semiconductors have the resistivity which is less than insulator and more than conductor. Okay, that means whenever the temperature varies, if the temperature is low, semiconductor will be having high resistance, no current will flow through it, and then it can behave like an insulator. When the temperature increases, resistance of the semiconductor decreases and it can behave as a conductor where there will be flow of electric current. Okay, this is a very important property of semiconductor. Then the same thing we'll see, that is the effect of temperature on semiconductors. Semiconductors have negative temperature coefficient. Negative temperature coefficient means if the temperature increases, the resistance has to decrease. If the temperature decreases, the resistance has to increase. So there we have given in the second para here, the resistance in semiconductors increases with the decrease in temperature and vice versa. This gives negative relationship between resistance and temperature, and that's why it is called as negative temperature coefficient. So semiconductors have negative temperature coefficient. Then if you go to see the conducting properties of a semiconductor, like now we know that as a temperature increases, you might get a few electrons which can be free and they can move and they can help you in conducting current. But there is one more method which is very important, and that method is mostly used in all the semiconductor devices. That method is only used in all the semiconductor devices. That is, if you read this sentence, the conducting properties of a semiconductor changes. Conducting properties means the amount it helps for the current to flow. The current conduction should take place. That can be changed when a suitable metallic impurity, that is your impurity, is added to it, which is very important property. So to a pure substance, a pure semiconductor, you are going to add a impure material. If you add a impure material, its conductivity will increase. Either it will increase the electrons in the semiconductor or it will increase the holes in the semiconductor, depending on what type of impurity you are adding. Then we'll go to see a classification of semiconductors. Semiconductors can be classified as intrinsic semiconductor. So here you can see It can be intrinsic semiconductor, which is also called as pure semiconductor, and for which examples are silicon, silicon and germanium, silicon and germanium. If you add impurity to this intrinsic semiconductor, you will get extrinsic semiconductor, which will be called as impure semiconductors. Okay. If you add a trivalent impurity, then you will get P-type semiconductor. If you add pentavalent impurity, then you will get N-type semiconductor. Okay, so this is the classification of semiconductors. Then we'll go to see what are this intrinsic semiconductor, that is germanium and silicon, two examples we have given, but what are they? A semiconductor in its extremely pure form is said to be an intrinsic semiconductor. The properties of these pure semiconductors are as follows. The electrons and holes are solely created by thermal excitation. Okay, only the temperature excitation will create electrons and holes in intrinsic semiconductor. The number of free electrons is equal to the number of holes. The conduction capability is small at room temperature. It is not helping you way out to make the current flow through it. In order to increase the conduction capability of intrinsic semiconductor, it is better to add some impurity. This process of adding impurity is called as doping. Okay, that means what we are telling here is, as a pure semiconductor, whether you take germanium or silicon, okay, at its pure form, at room temperature, its conduction capability or its feature or its capability to make the current to flow is very small, and it is not useful when you use that material in any application as a semiconductor device. Therefore, to increase its conductivity, to increase its ability to flow of current, we have to add some impurity to this intrinsic semiconductor. And this process of adding impurity is called as doping. Okay. So here we will see what is doping. Doping is the process of adding impurities to the semiconductor materials. So the impurities added are generally of two types. One is pentavalent and one is trivalent. Now what is this pentavalent? Pentavalent are the atoms which have 5 valence electrons. Pentavalent are the atoms which have 5 valence electrons. That means there are 5 electrons in its outermost orbit. And a trivalent is an atom which has 3 valence electrons. 3 valence electrons. That means it has 3 electrons in the outermost orbit. Whereas your pure germanium and silicon have 4 valence electrons. 4 valence electrons, and they are called as tetravalent. Okay, that means your pure semiconductors will be tetravalent in nature. That is, they will be having 4 valence electrons. And the impurities which you are going to add to this germanium or silicon can be pentavalent, that is 5 valence electrons, or it can be trivalent, that is 3 valence electrons. Now what happens when you add a pentavalent impurity, and what happens when you add trivalent impurity? Now the process here is very clear. We are going to add impurity to the pure semiconductor. We are going to add impurity to the intrinsic semiconductor. Now once you add impurity to the intrinsic semiconductor, then intrinsic semiconductor will improve its conduction property, and it is called as extrinsic semiconductor. So that we will see what happens when we add pentavalent impurity and what happens when we add trivalent impurity. So pentavalent impurities, The pentavalent impurities are one which has 5 valence electrons, as I've told you, in the outermost orbit. Examples of this will be bismuth, antimony, arsenic, phosphorus. The pentavalent atom is called as a donor atom. Now remember this, it is called as donor atom because it donates one electron to the conduction band of pure semiconductor atom. Means what is happening, that we can see in a figure what I'll show you afterwards. Then we'll see what are trivalent impurities. Trivalent impurities are the ones which has 3 valence electrons in the outermost orbit. Example, gallium, indium, aluminium and boron. The trivalent atom is called as an acceptor atom because it accepts one electron from the semiconductor atom. Now this also I will show you with the help of crystal pattern. Then we will see the definition of extrinsic semiconductor. An impure semiconductor which is formed by doping a pure semiconductor is called as an extrinsic semiconductor. There are 2 types of extrinsic semiconductors depending upon the type of impurity added. Now they are called as N-type semiconductor, N-type extrinsic semiconductor because you are adding pentavalent impurity, and P-type extrinsic semiconductor because you are adding trivalent impurity. Then what is N-type semiconductor? N-type extrinsic semiconductor, a small amount of pentavalent impurity when it is added to a pure semiconductor to result in a N-type extrinsic semiconductor. The added impurity has 5 valence electrons. For example, if arsenic atom is added to the germanium atom, 4 of the valence electrons get attached with the germanium atoms while 1 electron remains free because germanium will have 4 valence electrons and 1 electron will become free. That we can show with a crystal pattern. So here we have shown, you can see you are having a germanium atom here. Okay, you are having a germanium atom here. You are having germanium atom here. You are having germanium atom here. You are having germanium here. And you are having germanium here. Now all this germanium will have 4 valence electrons in the last orbit. So this is 1, 2, you can have here 3 and 4. Similarly here 1, 2, 3 and 4. Similarly here 1, 2, 3, 4. Here 1, 2, 3, 4. Here also 1, 2, 3, 4. Here also 1, 2, 3, 4. Here also 1, 2, 3, 4. And here also 1, 2, 3, 4. Okay. Now we have added an impurity called as arsenic. So here you can see an arsenic atom in the center. Now arsenic is what type of impurity? It is a pentavalent impurity. So it will be having 5 valence electrons. Now out of those 5 valence electrons, 4 electrons will make a covalent bond with the adjoining germanium atoms. So 1 electron will make a bonding with this electron. Another electron will make a bonding with this electron. Another electron will make a bonding with this electron. And another electron will make a bonding with this electron. So 4 electrons will make 4 bondings with their adjoining germanium atoms. But the 5th electron, where it has to go? The 5th electron becomes free. The 5th electron becomes free. It has no chance of bonding with anyone because arsenic was having 5 valence electrons. It was a pentavalent impurity. Now it has been joined. It had been added with germanium atom. Germanium is having 4 valence electrons. So out of this 5, 4 make a covalent bond and 1 electron becomes free. This is becoming free. Now this electron can be used for a conduction, for a current to flow. Okay. Now when you add a small amount of such impurity of arsenic, many such free electrons. If you add a very small amount, many such free electrons can be produced. Okay, and because it is giving free electrons, it is called as donor. Donor. It is giving you a free electron. And these free electrons are used for your conduction of a current in that particular semiconducting materials. And because here you are producing more of free electrons, negative charge particles, it is called as N-type semiconductor. Then here you can see the theory. All of these free electrons constitute electron current Hence, the impurity when added to pure semiconductor provides electrons for conduction. In N-type extrinsic semiconductor, as the conduction takes place through electrons, the electrons are called as majority carriers. And because there might be some holes or because of a temperature excitation, they are called as minority carriers. As there is no addition of positive or negative charges, the electrons are electrically neutral. When an electric field is applied to an N-type semiconductor to which a pentavalent impurity is added, the free electrons which are produced will travel towards the positive electrode. They will flow towards the positive electrode. This is called negative or N-type conductivity. Then we'll go to see P-type extrinsic semiconductor. Now here, the impurity which we are going to add will be trivalent. Okay. A small amount of trivalent impurity is added to a pure semiconductor to result in P-type extrinsic semiconductor. The added impurity has 3 valence electrons. They are trivalent elements. For example, if a boron atom is added to the germanium atom, 3 of the valence electrons get attached with the germanium atoms to form 3 covalent bonds, but 1 electron will become short. So one more electron in germanium remains without forming a bond, as there is no electron in boron remaining to form a covalent bond. This space is treated as hole. This we can see with this pattern here. So here you can see you are having a germanium atoms all on the sides. You can show the germanium atoms. So here you can see a germanium atom. It is having 4 valence electrons, 1, 2, 3, 4. Here also you can see germanium atom. It is having 4 valence electrons, 1, 2, 3, 4. Here also you can see germanium with 4 valence electrons. Here also you can see a germanium atom with 4 valence electrons. Here also you can see a germanium atom with 4 valence electrons. Here also you can see, here also you can see, and here also you can see. Now to this germanium atoms, we have added a small amount of trivalent impurity, which is called as boron, which is shown in center. It is trivalent impurity because it has only 3 valence electrons. So out of those, these 3 electrons will make a covalent bond with the adjoining germanium atoms. So this first electron will make a covalent bond here. This second electron will make a covalent bond here with the germanium. The third electron will make a covalent bond here. But boron has no 4th electron. So here you cannot make a bond, no bond here, no bond here. So you cannot make the 4th bond. Whereas the germanium is having the 4th valence electron, but your boron impurity which you are adding is trivalent. It is having only 3 valence electrons. So this place will remain empty. This place will remain empty. And this empty space will be called as hole. Will be called as hole. So here, if you add a small amount of such a trivalent impurity, you can produce many such holes. And because the hole is considered as an absence of electron, because the hole is considered when electron is not there, that empty space is considered a hole. Then if electron is negative charge, then hole we are going to consider as positive charge. Okay, so if you add a small amount of such a trivalent impurity, you can produce lot number of holes, and that type of material will be called as p-type extrinsic semiconductor, in which holes will be the majority charge carriers and help for the flow of current. You can also have electrons, free electrons, due to thermal energy, which can be minority charge carriers. So here you can see the theory. The boron impurity when added in small amount provides a number of holes which helps in the conduction. All of these holes constitute hole current. In p-type extrinsic semiconductor, as the conduction takes place through holes, the holes are majority carriers, while the electrons which are away because of temperature are called as minority carriers. The impurity added here provides holes which are called as acceptors, because they are acceptors. They are not donating electrons, they are accepting, because they accept electrons from the germanium atom. As the number of mobile holes, that is moving holes, remains equal to the number of acceptors, the p-type semiconductor remains electrically neutral. When an electric field is applied to a p-type semiconductor to which a trivalent impurity is added, the holes travel towards the negative electrode. This is called as p-type conductivity. Then what is a diode? We will see formation of PN junction diode. If a p-type and an n-type material are brought close to each other, both of them will join to form a junction. And that junction will look like this. So here you can see you are having a p-type material here. This is your p-type material, this is n-type material, and this is the junction. So this is your PN junction, PN junction. Okay, so this is a p-type material is joined with n-type material. Now at this case, what happens? The p-type material is having holes, that is positive carriers as majority carriers because you're adding trivalent impurity. And n-type material will have electrons as majority charge carriers because you're adding pentavalent type of impurity. Okay. And when you join them, the electrons will be attracted by the holes here and they start moving here. And the holes will be attracted by electrons here and then start moving here. So this movement takes place, the crossover takes place. And it will take place for some time until a depletion layer is formed in between. Okay, so here we can see the theory. A p-type material has holes as the majority carriers and an n-type material has electrons as majority carriers. As opposite charge attract, few holes in p-type tend to go to n side, whereas few electrons in n-type tend to go to the p side. This is what we have told. As both of them travel towards the junction, holes and electrons recombine with each other to neutralize and form ions. So holes and electrons will recombine with each other and they can form ions. Now in this junction, there exists a region where the positive and negative ions are formed, which is called as PN junction or junction barrier. So here you can see the electrons from N side were initially moving towards P side and holes from P side were initially moving to N side, and then they got recombined. They got combined with each other because of attractive charges. One was positive, one was negative, and in that process they formed ions. So here on the p side layer you can see the ions which are formed are negative ions. Negative ions here, those are not movable charge carriers. They will not help you in current to flow. And you can see on the n side near the junction there are positive ions formed. Positive ions formed. Okay, now these ions are not movable carriers. Okay, they are only fixed carriers which will form an electric field here, and this will be an electric field here. We can have plus minus electric field. Now this electric field will be developed because of the ions which are present at the junction of PN, and that will be your barrier. That will be a opposite potential which you have to overcome whenever you want this formation to conduct. Then you can see the theory here. The formation of negative ions on p side and positive ions on n side results in the formation of a narrow charged region on either side of the PN junction. This region is now free from movable charge carriers. The ions present here have been stationary and maintain a region of space between them without any charge carriers. As this region acts as a barrier between the p and n type material, this is also called as barrier junction. This has another name called as depletion region, meaning it depletes both the region. It will make the main charge carriers less and the ions will be more, so there is no current conduction. There occurs a potential difference Vd due to the formation of ions across the junction called as potential barrier, as it prevents further movement of holes and electrons through the junction. Then what is biasing of diode? Whenever you make a PN junction formation, that formation will be called as a diode. It is a semiconductor diode. So here you can see if you are having p-type material and n-type material. Okay, this is p-type, n-type material. There will be a depletion region formed here. So here you can have one terminal, here you can have one terminal. This terminal will be called as anode and this terminal will be called as cathode. And this is nothing but your semiconductor diode whose symbol can be shown like this. This is your anode, this is cathode. Okay. And the arrow mark is showing the flow of conventional current. Now, how is this going to be biased? How we are going to apply voltage to it, and applying voltage to it, what kind of bias you will get, what kind of conduction you will get, whether it is going to conduct forwardly or whether it is going to conduct reversely. Okay, so here you can see the definition. When a diode or any two terminal component is connected in a circuit, it has two biased conditions with the given supply. Depending upon the supply and whatever you are applying. Okay, so if you apply the supply like this, positive terminal to the p type and negative terminal to the n type, then it is called as forward bias. If you apply the opposite way, say if you are having p and n here, pn, and if you apply negative terminal to the p type material and positive terminal to the n type material, then it will be called as reverse biased. Okay. So therefore, there are two conditions. One is forward bias condition and one is reverse bias condition. Then here you can see forward bias and reverse bias with symbol of diode. So here we have shown the symbol of diode. So this is your symbol of diode. Okay, this is nothing but your PN junction. This is nothing but your PN junction. Okay, PN. And here is your anode and here is your cathode. So when the anode is connected to the positive terminal of the battery and cathode is connected to the negative terminal of the battery, then it is called as forward biasing condition. Similarly, when you connect anode to the negative terminal of the battery and cathode to the positive terminal of the battery, it will be called as reverse bias condition. Okay. Then what is forward bias condition? When a diode is connected in a circuit with its anode to the positive terminal and cathode to the negative terminal, as we have seen, of the supply, then such a connection is said to be forward bias condition. This kind of a connection makes the circuit more and more forward biased and helps in more conduction. Diode conducts well in forward bias condition. Then what is reverse bias condition? When a diode is connected in a circuit when its anode to the negative terminal and cathode to the positive terminal of the supply, then such a connection is called as reverse bias condition. This kind of connection makes the circuit more and more reverse biased and helps in minimizing and preventing the conduction. That means current will not flow much. Diode cannot conduct in reverse bias condition. Okay, so there will be no flow of current in reverse bias condition. Then what is the effect of temperature on this current conduction, whether it is in forward bias or reverse bias? A current that a PN junction diode can conduct at a given voltage is dependent upon the operating temperature. An increased temperature will result in large number of broken covalent bonds, and that will increase the large number of majority and minority carriers, and this amounts to a diode current larger than its previous diode current. So if the temperature increases, the diode current increases. The above phenomena applies to both forward and reverse current, whether you are having a forward bias junction or whether you are having a reverse bias junction. In both the cases, if the temperature increases, the amount of current flow will increase. Thank you, students.